Wonderful. Again, good morning, good afternoon, and good evening, distinguished colleagues. Thank you for attending our webinar today. Leonardo Energy webinars are a very unique and a truly global meeting space for energy professionals, and I would like to welcome you here today. My name is Alex Pavlovsky. I'm president of Green Power Labs, a Canadian solar energy company, and I'm going to talk to you today about a comprehensive decision support for using solar energy in community energy planning and the broad deployment of solar energy technologies. About today's presentation. The overall objective of this webinar is to provide you with a holistic vision and clear step-by-step action plan for assessing the role of solar energy generation in community energy mix, followed, of course, by appropriate deployment of solar technologies. We would like to present to you three major stages and three integral parts of solar energy assessment for community energy planning: comprehensive solar resource assessment based on historical and current solar climatology data, community solar suitability mapping, and solar assessment of individual buildings. Briefly about Green Power Labs. We are a company of solar resource experts and engineers. As solar resource experts, we provide global solar resource assessment, mapping, and forecasting services. As solar engineers, we assist our clients with assessment, planning, and implementation of solar energy generation systems. Established in 2003, the company has evolved into a leading solar expert and has built a reputation for exceptional quality of knowledge base and service. We are an Atlantic Canadian company, and very often we are asked, why solar? Come on, this is Canada. What are you actually talking about? And we are so rich with energy here. Well, are we really? And are we happy with our inevitably growing energy bills? Should we look around and consider using an energy source that is already ours and free? Should we consider energy technologies that match our own community needs in heat, cool, or power? The natural answer is yes, of course, and we immediately turn to the sun. Both distributed on-site and centralized utility-scale solar heat and power generation technologies are mature today. I'm not going to overload you with figures on the state of solar industry. All these figures are readily available from many sources, for instance from the International Energy Agency. Only few milestones of solar PV industry in 2007. The annual rate of growth of cumulative installed capacity was over 40%. And of this total capacity installed in 2007, only 6% were off-grid projects. So we saw the threefold increase in grid-connected centralized capacity. This reflects the growth in investor-owned large-scale PV power systems being developed in response to the fit-in tariff frameworks in place in a number of countries. Today, solar technologies are readily available to the general public, and while lots of work is still being done on the improvement of technology efficiency, the major problem is not the absence of technology. It is at our hand actually, reliable, clean, and cost efficient. Solar water heating technologies are available and applicable in most areas worldwide. And in solar power generation, we are rapidly moving towards grid parity. Solar technologies bring energy security, self-sufficiency, reliability, and finally, zero carbon emissions. But the major problem today, as we see it, is not technology, it is the information gap between the technology and its users, architects, engineers, building owners, and managers. Today we see the major need in quality decision support for solar generation deployment, clear and simple routine that demystifies solar industry and advises on the most efficient way to include solar generation into the community energy mix. In order to make solar energy generation systems massively deployed in communities worldwide, we need to make their performance predictable and tangible. With any technology deployment, the devil is in the detail. We need to know how much solar energy we have in this or that area and what is the share of this energy flow that will be taken away from us by local microclimate like morning fogs in San Diego or coastal fogs in Nova Scotia, landscape, built environment, our own building design, and finally solar technology efficiency. All these are very much filters that take solar energy away from us, and we need to describe these filters in much detail to define our true solar share, the amount of energy that we could rely on annually in our energy mix. In order to do this, we propose a three-stage approach that I will be walking you through. The stage one is solar resource mapping based on historical and current climatology trends. We need to know our solar energy asset, to know what has been happening with solar resource in the recent 10, 20, 30 years, and of course, to know what is going on with this resource today. In order to provide answers to these questions, we built good quality, high-resolution solar resource maps. When we define historical trends in solar climatology, we use best available sources of surface meteorology and solar radiation data. Those are NASA World Radiation Data Center, National Climatic Data Center, and so on. Our interactive SolarGIS map sets include global horizontal solar radiation data, direct, normal, and diffuse irradiance for every month of year, and annual totals. On this slide you see a historical solar climatology map of Nova Scotia. We work on some other data sets for many provinces in Canada, and this slide shows the high-resolution solar map of Quebec. Finally, the high-resolution solar map of Ontario, a critically important knowledge base for communities and solar power developers in this province because of a coming green energy law and the promise of long-term incentives for producers of renewable power in Ontario, with up to 80 cents Canadian per kilowatt hour generated on building rooftops. It's now not enough to understand the historical trends in solar climatology, whether it's spatial distribution of solar resource across a region, or monthly or diurnal variation of solar irradiance. Permanent climate change makes it important to know the current solar climatology. To address this need, Green Power Labs has developed a satellite-based solar resource monitoring toolset. Our solar monitoring technology allows to put in virtual pyranometers in every square kilometer of the global surface, and to monitor solar resource with high temporal resolution, which very much depends on the satellites we use. My colleague Dr. Vlad Kostel was presenting our monitoring technology to Leonardo Energy audience in February 2009, and his presentation is available online. This slide illustrates the use of satellite-based solar resource monitoring for community energy mapping. This map was built for community energy mapping project in Strait Highland region of Nova Scotia based on 2007 satellite data. Alright, we know now everything about solar resource. Our next task is to properly describe the filters that take a part of this resource away. In other words, to assess solar suitability of our target community. And as an example of community that is in process of its energy planning, we used Dalhousie University campus in Halifax, Nova Scotia. Dalhousie is an oldest university in Canada. It was founded in 1818 by the 9th Earl of Dalhousie and awarded its first BA degree in 1866. It has over 60 facilities, and each of them requires energy management. There are several drivers that facilitate Dalhousie campus energy planning. The first is its sustainability plan, promoting approaches and decisions that improve the campus and local community ecology, economy, and health, of course. The second is a new Dalhousie master plan that is currently being developed and that supports the university's strategic direction in sustainable development. Campus energy planning is an integral part of Dalhousie master planning process, and Dalhousie campus solar suitability assessment was a very important stage in this development. Quality solar suitability assessment of a community requires special technologies. Here we need a toolset that will allow us to determine what part of what facility roof or wall will be more suitable for solar energy applications. How much more, and for what technology? For ultra-high resolution solar resource maps of the campus, Green Power Labs used LIDAR survey. LIDAR, light detection and ranging, is an optical remote sensing technology that measures properties of scattered light to find range and or other information on a distant target. We use airborne LiDAR data to build an ultra-high resolution 3D models of communities that allow us to develop high-quality solar suitability maps. The slide presents a solar suitability map of the Studley campus of Dalhousie University, one of the three major university campuses. The mapping accuracy here is about 20 centimeters. Orange color indicates the high resource areas and blue low resource areas. Such a map is a core component of community solar deployment decision support. It tells you with much certainty what buildings are most suitable for solar energy applications at a surprising detail level. Using LIDAR-based solar suitability map of the campus, we are able to rate every facility for its suitability for solar energy applications. In our analysis, we use Solar Star suitability rating, a rating standard that was developed by Green Power Labs in collaboration with our architectural partner WHW Architects. On the next slide you see the results of Solar Star rating visualized in a map format. It makes very clear for the campus facility management team where to go first in their plans to deploy on-site solar energy generation. LIDAR-based solar suitability map allows also for determining solar energy generation potential of each campus facility. Here on the slide you see solar water heating potential for each campus facility. Comparing it with service domestic hot water consumption, we define so-called solar fraction, the share of energy that is required for service water heating that will be provided by the sun. The same type of maps we build for every applicable solar technology. The next slide shows solar space heating potential of the campus facilities. In Atlantic Canada, space and water heating may take over 80% of energy budget. So understanding the role of solar energy in active space heating is critically important for campus energy planning. The table on the screen shows the final results of solar energy generation potential assessment for Dalhousie campus. It was shown that using building roof surfaces mostly for solar water heating and building walls mostly for solar air heating, it is possible to provide over 21% of the campus heat imbalance by solar energy generation. Alright, now when we know solar features of every building in our community, we can choose the best candidates for solar technology deployment and drill down further. For these best candidates, we will do a site-specific suitability assessment. We will analyze these candidates in detail, understand their individual energy mix and critical energy needs, pre-engineer applicable solar energy systems, determine their performance, cost, and finally, return on investment. We believe that site suitability assessment is a stage that crowns a comprehensive community solar suitability journey and is a mandatory step in efficient deployment of solar technologies. It creates a unique solar passport for the assessed facility and very much paves the way to actual system installation and commissioning. The pictures on this slide show a building that is not a part of the Dalhousie campus and is located in the other part of Nova Scotia on the shore of the Bay of Fundy, the shore with the highest tides in the world. This is Fossil Cliffs Interpretive Center in Joggins, Nova Scotia. Joggins Fossil Cliffs are regarded as the best record of life in the coal age 300 million years ago. I would like to promote this building because I love the design and also because it played a key role in having Joggins Fossil Cliffs designated a World Heritage Site by UNESCO. Also, the Interpretive Center building showcases the full solar suitability cycle, where after a thorough resource assessment, we conducted solar suitability assessment of the building architectural design, the upper picture, and then engineered and commissioned its solar PV system, the lower picture of the actual building. When we come to solar system engineering, the results of all the three stages of our solar suitability assessment are immediately tied together. The pictures on the slide showcase this link. The charts show solar energy resource as a function of solar collector slope and azimuth, and indicate the slope and azimuth ranges that maximize available solar energy. As we know, solar collector slope and azimuth are critical to solar system design. The pictures illustrate how different is the distribution of solar energy available for different microclimates. One where direct radiation prevails, and the other where prevailing diffuse radiation. And what is the best relation between collector azimuth and slope for each of these cases? As at the previous two assessment stages, when conducting site suitability assessment, we also use a very special toolset. A key component of this toolset is a fisheye lens with over 180 degrees of field of view that allows for complete covering of the sky hemisphere. This lens is used to provide a quality analysis for the existing obstructions to solar radiation for solar suitable building surfaces. The images are then processed by a proprietary software tool calculating so-called obstruction factor, a share of energy taken away by existing obstructions. The results allow for a correct calculation of solar energy available for solar technology applications. Now we are back to Dalhousie University campus, applying our site assessment toolset. I will talk here about two examples of site suitability assessment for two good candidates for solar energy applications at the campus: Sir Charles Tupper Building and the Killa Memorial Library Building. This is Sir Charles Tupper Building. As you see, it has two major parts, one low-rise, another is high-rise. The roof of low-rise part was considered for solar water heating application, and a wall of the high-rise for solar air heating. The fisheye view to the left was used to determine obstruction factor for solar water heating system positioning. The red line on this image shows the sun pathway on the 21st of June, the highest position of the sun, and the blue line on the 21st of December, the lowest position. The chart on this slide shows the performance, carbon emissions reduction and payback period for both solar energy systems proposed. The picture shows also the proposed positioning of solar air heating system on the building wall. The same approach has been applied to the Kila Memorial Library building. Two solar energy systems addressing heating energy balance of the building were assessed. The solar water systems on the building roof and the solar air heating system on the south-facing building wall. The results are shown in the chart. The proposed systems can meet over 40% of domestic hot water and space heating energy balance for this building. Now, when we're done with the heavy artillery of our toolsets for solar suitability assessment, I would like also to introduce you to our lightest tool, SolarRating Online. This tool has been developed as an educational tool for schools, colleges, and the general public to promote the critical knowledge needed to plan the use of solar energy systems. This is an interactive and very fun tool. You are most welcome to visit our website to try it yourself. This is in a nutshell how we approach solar suitability assessment for community energy planning. We start with a comprehensive solar resource map. Then we rate every community building for its solar suitability and define its solar energy generation potential. We choose the best candidates, pre-engineer solar systems for them, and calculate the return on investment. By this, we create community solar IDs that communities and building owners will be using in their long-term energy planning. From now on, all decisions on solar deployment are informed, and solar energy and technology is no more a mystery, but an available and sustainable source. Thank you very much for your attention, and questions please.
Okay, great. Alexander, please remain with open microphone just to be sure we don't have any additional technical problems.
Yep.
Good. So, well, we will proceed to Q&A session. So we start with a question from Ricardo Battisti. What about assessments at a wider level? For instance, municipality or region? Are the same tools of showed suitable and reliable? Thank you.
Yes, the answer is yes. So well, the tool set presented incorporates regional solar resource mapping and municipal solar suitability mapping. So at each level the results showed very high level of reliability and quality. So we could assess solar resource regionally. We can assess suitability of this or that community using LIDAR-based technologies, and then we could drill down to individual buildings. So all three tool sets that are interlinked, of course, show the very high level of reliability.
Okay, great. Thank you very much, Alexander.